I am so pleased to be here, able to present to this wonderful audience at MIT. I regret that we can't all be together, but I'm sure this is a much safer route. This is a very important topic that MIT has chosen to tackle this year, the issue of climate change and energy. The material that I'm going to be presenting to you today is, of course, not my own work, but it is the combined work of a number of very distinguished committees who have addressed these questions on behalf of the National Academies of Science, Engineering, and Medicine. And the title of my presentation is shown here on this slide, Tackling the Hard Stuff, Game Changers in Climate and Energy Systems. So if I can get these slides to advance here, which they don't want to do. Here we go. Here are my key messages, just so that you know where this talk is going. And if any of you tend to nod off in the presentation, you'll know where I'm going to end up. I've got 5 key messages for this presentation. First of all, we are literally cooking the planet with global warming. And today's energy system is the biggest source of emissions that are causing climate change. The good news is we can make some easy changes today. We've got technical solutions that are known. But some of the parts of the problem will be hard, either for technical reasons or because of the challenges in people, processes, and institutions. And in my view, the technical problems may actually be the easier ones to solve, that the people problems, the process problems, and the institutional problems could be the more difficult ones. And fourth, we need to invest in developing game-changing solutions that, with some luck and ingenuity, can help us make those hard problems seem easy. And finally, we will go further and do better if we include all people in our approaches. Okay, now this is a familiar picture. It is the lights as seen from space. And the problem is, while energy, we all agree, is terrific, it allows us to have our quality of life and do the work we want to do, but fossil energy does pollute. As we can see from this slide, these are pixels from a NASA image. We see strings of cities and also the transportation networks that connect them. We even see from space gas flaring from oil and gas development. Energy use is essential, but our modern energy system is polluting our planet with greenhouse gases. Now, let's start with the easy stuff. There are 3 things we can do today that are low-hanging fruit. We can decarbonize electricity generation, and along with that, we can electrify more end uses. And third, we can reduce energy demand while increasing value, comfort, and convenience. And I'll give you some examples of all of those. First of all, what we can do today to decarbonize energy generation. These are some examples where fossil fuels are burned for space heating, water heating, industrial processes, releasing CO2. Some of these processes are relatively easy to electrify, including space heating in homes and businesses via electric heaters, heat pumps, and heat and power. We can also go to wind energy, solar energy, etc., in order to decarbonize electricity generation. We see a nuclear power plant here, which is also, of course, a carbon-free method of producing energy. Furthermore, this is a map that shows of how we can electrify end uses. This is just an example of building heat that shows across the US the different kinds of building heat that is in use today. You see in the Northeast that it's largely fuel oil or other, which is probably wood stoves, etc. Whereas in the Southeast, it's already mostly electric, as well as in the Pacific Northwest. Through the Midwest and parts of California, we have LPG, and in many areas, there's also natural gas that's piped into homes. So this shows that we have a lot of room to grow in terms of electrifying just building heat. Now, also among the easy stuff is reducing energy demand, for example, through efficiency. Now, this plot shows in the blue line on the top how from 1972 up to 2016, which is on the right, how the volume in cubic feet of refrigerators has increased. Not a lot, but to some extent. At the same time, the energy demand from those refrigerators has dropped precipitously from, in the units here, 2,000, and the units are kilowatts per year, down to a quarter of that, down to 500. And at the same time that the energy demand from those refrigerators has plummeted, so has the price. So this is a win-win-win situation. We can have bigger refrigerators that use less energy at lower cost. And you can imagine that this type of curve can be replicated with other electric appliances. Oops. Now let's move to some of the hard stuff. Let's look at the technically hard stuff. Technical challenges remain significant for distributed emissions in transportation, in agriculture, for intense duty cycles like freight and air transport, and in high temperature industrial heat, and for the greenhouse gases released as part of chemical reactions, for example, in producing steel and cement. These are all areas which are much more difficult to find easy solutions for. And there's also logistical challenges. Even when technologies are known, logistical challenges lie in building out the infrastructure, in implementing technologies because they cost more upfront than the higher carbon emitting technologies. And also there are logistical challenges in motivating consumers when they have no financial incentive to purchase a lower emitting technology. Right now we've seen low fossil fuel prices, which leave little consumer incentive to switch to example, to renewable electricity. So how much is reasonably easy with the technology we have today? Well, surprisingly, about 70% we can do with technology we have today. The easiest stuff is about 30% of emissions, which is decarbonizing electricity generation and efficiency improvements. The moderately easy stuff is another 40%. For example, light duty vehicle transportation, some building and industrial electrification. So that leaves only about 30% that is hard to do with the technology we have today. And so focus has to be on developing the game-changing technologies to make it easier, and that should be the focus for investments to provide our future options. So let's look at game changers to take the US to zero net emissions. So people need energy to do almost everything they want to do. Investment in research and development of new technologies can give us options to use energy to reduce emissions to zero. Growth in institutions, people, and processes can facilitate the development and commercialization of those technologies in the market. But there are challenging problems in distributed emissions, the difficult duty cycles, which I mentioned, and developing solutions in technologies, institutions, people, and processes. Those are where we need the game changers. So where might we look for some of these game-changing technologies? We can look in algorithms and other means to maintain grid reliability with intermittent renewables. We know that the sun isn't always shining. The wind isn't always blowing. How do we compensate for that? We need to look at advanced nuclear electricity generation. I don't have to repeat to this audience what the concerns are about the current generation of nuclear power plants. We can look for net zero carbon liquid fuels, and I'll talk a little bit more about that, and negative emissions technologies, which I'll also talk more about that. So algorithms to maintain grid reliability with intermittent renewables. So renewable generation is one of the major keys to decarbonizing the grid, but it represents reliability challenges and the need for storage, better batteries, for example. But algorithms can provide functionality to maintain safety and reliability. There's the potential to create, for example, something called virtual storage through coordinating building loads, EV charging and discharging, so that we don't have to actually really store things, but just balance the load in ways such that we're smart about how we use that renewable energy. And we can use machine learning with self-improving algorithms and artificial intelligence. That all has future potential. But all will necessitate cybersecurity considerations and improvements. We've all heard of some of the hacks on power generation facilities and how vulnerable we can be to those. So we can't forget about cybersecurity. Now, grid integrated buildings offer the ability to shift electrical load to meet supply. So we imagine the old days where a building just connected to the grid and it pulled power from it. Now, grid integrated buildings are smartly integrated to the grid such that they are efficient, they're connected, they're smart, and they're flexible. They are persistent in their low energy use. They minimize demand on grid resources and infrastructure. They're also connected two-way with flexible technologies to the grid, between the grid and the occupants. They're smart. Analytics are supported by sensors and controls that co-optimize efficiency, flexibility, and the occupant preferences. And they're flexible with loads and distributed generation storage can be used to reduce, shift, or modulate energy use. You imagine one person in an office is always too hot, the person in the office next door is too cold. There's no need to turn on the air conditioner for one person and the heater for the other person if you can balance the heat appropriately. Now, advanced nuclear electricity generation is also an important thing to look at. I haven't seen any route to maintaining below 2 degrees global warming that doesn't involve continuation of nuclear power generation. Nuclear is currently 20% of the generation of power in the US. And the important thing about nuclear is that nuclear is almost always on. If you look at the capacity factor by the different source, Nuclear has the highest capacity factor of all of the other energy sources, meaning that nuclear power plants are producing close to maximum power more than 93% of the time, whereas natural gas is only at 56%, coal at 47%, hydropower 39%, wind 34%, solar 24%. And wind and solar have such low factors of capacity because of the amount of time the sun is shining and the amount of time the wind is blowing. So if you need to replace nuclear with other no carbon sources, you have to create a lot of solar and a lot of wind to replace that nuclear. Now, if you look at US electricity generation by source on the right side of the slide, you see that nuclear is kind of slowly projected to decline in the future, while non-hydropower renewables are projected to go up, but they have to go up a lot to compensate for any loss in nuclear. Furthermore, if you look at the age profile of nuclear power plants in the US, with the United States on the top, the red bar is those plants that are over 30 years old, and the blue is less than 10 years old. You see, for example, compared to China, how old our fleet of nuclear power plants are. If we don't look at renewal of nuclear generation very soon, we will be rapidly losing capacity of a type of power that produces no net CO2, or actually no CO2. So advanced nuclear electricity generation is an area of intense research right now. Now, the Nuclear Regulatory Commission regulations are based on what are called light water reactors. And these are basically glorified steam producers. The reactor core heats circulating water that ultimately becomes steam, that rotates a turbine, that generates electricity. These reactor designs have very high capital costs, long deployment timelines, and large space requirements. They must abide by rigorous safety regulations, and they cannot be close to high population areas because of that. Thus, they require large investment in transmission infrastructure to get the power from their siting to where it's needed. Now, advanced nuclear electricity generation has to compete with natural gas right now if it's going to be economically viable. This diagram shows the net additions and retirements in natural gas as compared to nuclear. Now, the solid brown bar shows the new natural gas power generation that's gone in, and the stippled brown, the ones that are projected. The dark blue, or the solid blue, shows mostly nuclear retirements and just like one addition. And the stippled blue shows a few nuclear additions, but mostly nuclear retirements that are planned. So you can see that it's quite obvious that nuclear is having a very hard time competing with natural gas. That makes the future of nuclear very uncertain, and marketplace concerns are the biggest problem. For this reason, new reactors are being designed as small modular reactors, which have nowhere near the space requirements of traditional reactors and therefore lower capital and safety costs. Many have passive safety features, meaning the reactor does not require any active intervention or electrical feedback in order to bring the reactor to a safe shutdown. Some designs are currently being considered by the NRC, and demonstration projects are underway. Most notable is the NuScale system, which will be demonstrated at Idaho National Lab with buy-in from Utah Associated Municipal Power System. So here's what in advanced nuclear electricity generation, the small modular reactors looks like. They have a pressurized water reactor, and they have lower capital costs. They're factory assembled, small siting requirements, and passive safety features. Now, here's the various generations. Now, Gen 2, which are the pressurized water reactors, the boiling water reactors, are already built. Gen 3, there are some that have been built by Westinghouse in China and the US. They have a simpler design. They have, but they're still boiling water reactors. The NuScale ones, which are the ones that are on the drawing board now, are furthest along in the regulatory process, but many other advanced reactors are in the works. These Gen 4 designs operate at higher temperatures, and they're using cooling media other than water. DOE recently announced the Advanced Reactor Demonstration Project, which aims to help some of these unique designs reach demonstration and potential commercialization. So these Gen 4 reactors are different. The regulatory landscape may have to be completely overhauled to accommodate advanced reactor concepts because of the difference of different cooling media in different types of fuel, most notably high assay, low enriched uranium, which is an enrichment level that currently isn't available in the US. And many advanced reactor companies are considering economic viability to be their #1 priority. So many are also designing their products to be small modular reactors with potential alternative applications and ability to cooperate with renewable energy sources. So in other words, when the sun isn't shining or when the wind isn't blowing, they're working in tandem. So let's go on to net zero carbon liquid fuels. Net zero carbon liquid fuels use water and captured carbon dioxide or waste biomass and renewable energy to generate liquid fuel replacements for fossil fuels. The fuels can be stored, transported, and used as needed. And when burned to do work or provide heat, these fuels release only the carbon dioxide originally used to make them. So it's a net zero carbon cycle. The net zero carbon liquid fuel process will use more energy than direct use of fossil fuels or electricity. So the uses are probably best when a liquid fuel is needed, and that's going to be prioritized because in addition to the energy from the sun to grow the plant feedstock, you also need to use solar energy to make the liquid fuel. So there's sun's energy or wind energy or whatever used at 2 places in this cycle. So there's probably going to be limited use of it, but it could help us get to net zero energy. Challenges, there are technical challenges, chemical catalysis to improve the selectivity, formation of the carbon-carbon bonds, biological process improvements in growth, treatment, carbon-free hydrogen, commercial drivers, of course, economic value, scale, market capacity, market penetration of these new fuels, and then supporting infrastructure and technology, new supply chains, transportation, energy and material inputs, renewable energy, H2, et cetera, particularly getting biological feedstocks that aren't going to compete with human consumption, etc. And then let me next go to negative emissions technologies. This is something that the Academy has looked into. The negative emissions technology are best viewed as a component of emissions mitigation portfolio, not technologies that are deployed once society completely eliminates emissions from all transportation, electricity, industrial, and other sources. Although, of course, I don't know when we'd ever get to that point. Removing CO2 from the atmosphere and storing it has the exact same impact on atmosphere and climate as preventing an equal amount of CO2 from having been released in the first place. In some cases, deploying negative emissions technologies may be cheaper and less disruptive than the actual emission reduction, particularly in difficult to reduce sources such as those associated with aviation, heavy industry, or agriculture. Now, this figure shows the potential role of negative emissions technologies in reaching net zero emissions. How large the negative emissions technologies need to be to meet the Paris Accord targets under this scenario shows, you show the red line of what greenhouse gas emissions would have to follow to stay below 2 degrees C. The yellow line shows the business as usual curve. The green area shows what we might be able to mitigate in terms of greenhouse gas emissions. And the area between that green area and the red curve shows what we might have to further mitigate using net zero emissions technologies. And it shows that the amount of that grows from a small wedge in the 2030 to 2040 area to a larger wedge out towards the turn of the next century. And those wedges are 10 gigatons of CO2 per year by mid-century and 20 gigatons CO2 per year by the century's end. So here are some types of negative emissions technologies and their potential. Coastal blue carbon, accelerated chemical weathering of rocks to store CO2, direct air capture of CO2, biomass energy with carbon capture and storage, afforestation or reforestation, and soil carbon capture. All of these are covered in Academy reports. Okay, and then let me go to game changers in institutions, people, and processes. As I've said, some of these are some of the harder things to do. We need new coalitions built of voters and consumers who demand low carbon lifestyles that also deliver health, safety, and opportunity. We need continent-wide transmission investments to build renewables to demand centers, to bring them to demand centers, a circular economy in carbon and all other materials, and fossil fuel dependent communities. We somehow have to deal with them. We have to give them other kinds of economic opportunities. Now, the new coalitions. Climate change, Climate change will impact all people on the planet, and the most vulnerable will suffer the most. People continue to want light, warmth, cooling, and work that energy provides, but new coalitions are building that tie together energy access and affordability for all, people's health and livelihood, and the environment. So let's look at the problem of the transmission. The location of renewable energy and generation facilities depends on where the sun shines, where the wind blows, where geothermal energy is, etc. But renewable energy without storage can't be turned on and off. So balancing renewable electricity supplies with demand loads can be done with energy storage, with improved forecasting, and with transmitting power over long distances. So this just shows where the transmission lines are right now. There aren't a lot of them, but also where we have various kinds of energy, where the biomass is, where the wind is, where solar thermal is, where photovoltaics are, tidal energy, hydrothermal, etc. And really, on nationwide, we have a lot of renewable energy in different parts of the country. So how do we balance it? So if the wind is blowing someplace, but the sun isn't shining somewhere else, we can get energy from where it's being created to where it's needed. So high voltage converters and lines can transport power thousands of miles with limited losses. Transmission helps balance disjointed electricity supply and demand, but interstate transmission projects have been politically challenging. Long distance transmission facilitates critical movement for decarbonized electricity. But as I say, it's been hard to do. Transmission planning is federal, but authority to site and build the lines typically lies with states. There have been difficulties with cost sharing as well. Interstate transmission projects really have to be dealt with in order to move this decarbonized energy. You can see that there are very few in the West where we have an abundance of low carbon energy. Now let's go to the circular economy and carbon. Of course, a holy grail is to find reuses of carbon. The current process, which is shown in the gray line, follows a take, make, use, dispose, pollute model. We take the fuel, we make something out of it, or we use it, we dispose it, and we have carbon pollution. A circular economy would reduce or eliminate pollutants, including emissions, by recycling them and making something else, using it, reusing it, remaking it, recycling. New technologies, processes, and institutions will be required to make that circular economy. So this comes from a recent report from the academies to identify the status, barriers, and opportunities for commercialization of technologies that utilize carbon dioxide waste gas. Promising areas include mineral carbonization and chemical and biological conversion. So mineral carbonization would include, for example, cement that is made from a waste CO2 stream, or chemicals and fuels that are made from waste CO2. That in the case of construction materials, it would be sequestering CO2 in long-term buildings. But of course, there are unique challenges for resource extraction depending rural American communities. There's a tax base from coal generation in the West that can result in huge tax base loss for rural communities. We need to consider fiscal policy reform to address the failings of current business models, regional and multi-sectoral coordination to reinvent the urban-rural social contract on energy service, and how to re-envision rural economic development through developing robust institutions, resilience, and useful infrastructure, rather than simply replacing old energy technologies with new ones. We can't solve the climate energy problems unless we solve it together. We need to make the solutions about jobs, about health equity, about environmental justice, about access to quality of life, and a future for everyone's children. Because these are values that everyone can agree upon. And if we bring everyone together into the discussion, we're much more likely to make progress on this. So with that, I will be happy to take questions.